All right, a great day to one and all. To motivate our topic for today, I would like you to take a look at this following example. Suppose I have 2 plus 4 plus 8 plus 16 plus and so on. If you could see, this series is in fact geometric, considering there is a common ratio. Take a look. If you divide the second by the first, 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. And since you have a common ratio which is 2, so this is a geometric. And since this is geometric, and since you are adding all the terms, then this is a geometric series. However, you could actually see from this particular case that you have a first term, but you don't have a last term, but there is an ellipsis. So this is telling us that there are infinite number of terms in this series, and this is an example of what we call infinite geometric series. So again, a great day to everyone. I am Mr. Kim J.C. Ensho, a faculty member of Iloilo National High School Special Program in Science, Technology, and Engineering, and I will present to you this topic for today, Infinite Geometric Series. So please stay with me, and I am hoping that you will be learning something out of today's discussion. When we speak about infinite geometric series, it is the sum of the infinite number of terms of a geometric sequence. And since we have infinite number of terms, we will denote its sum by S sub infinity, where S sub infinity is equal to the sum of the first, second, third terms, and so on. So in this time, there is no end to the terms that we are adding. And this time, I will be defining to you two types of geometric series based on the values of the common ratio. The first one is what we call converging geometric series. A certain geometric series is converging if it has a common ratio whose absolute value is between 0 and 1. For example, 1/2, 2/3, 1/3, negative 2/5. Even if it's positive or negative, as long as if its absolute value is between 0 and 1, then the series is converging. And note that 0 and 1 as common ratios are not included. And when we speak about diverging geometric series, it is a geometric series which has a common ratio whose absolute value is greater than 1. Be reminded that for our context here, we will be dealing with infinite geometric series. So this time, let's have a quick exercise. Identify the common ratio of each geometric series and state if the series is converging or diverging in the context of this infinite series. For example, if I have negative 5 plus negative 10 plus negative 20 and so on, you could see that if you divide negative 10 by negative 5, that's positive 2. Negative 20 divided by negative 10, it's 2. So you see, the common ratio here is 2, and the absolute value of 2 is greater than 1. Hence, this series is diverging. How about for the second case? Negative 729 plus 243 minus 81 plus 27 minus and so on. If you will divide the second by the first, the third by the second, the fourth by the third, and so on, you could actually check with the help of your calculators, if you wish, that the common ratio is negative one-third. And since the absolute value of negative one-third, which is one-third, is between 0 and 1, so this infinite geometric series is converging. How about the third one? 27 plus 18 plus 12 plus 8, and so on. If you divide 18 by 27, 12 by 18, 8 divided by 12, you will get a constant ratio or a common ratio of 2/3. 2/3, its absolute value is between 0 and 1. So this series is again converging. How about 4 plus 4 squared plus 4 cubed plus 4 to the fourth plus 4 to the fifth plus dot, dot, dot. So if this is the case, 4 squared divided by 4, 4 cubed divided by 4 squared, 4 to the fourth divided by 4 cubed, 4 to the fifth divided by 4 to the fourth will give you a common ratio of 4. And this is higher than 1. So D here is a diverging series. And lastly, how about if you have this sequence first? But for now, let's make it a series. How about this? Using your calculators and using a similar process, you could actually see that your common ratio here is negative 5/2, or that's negative 2.5. Getting the absolute value of negative 2.5, you have 2.5, which is greater than 1. Hence, this series is diverging. I hope I was able to make it clear to you. Feel free to pause the video from time to time if you wish to reflect or to solve on your own as well. All right. So I hope there are no questions about converging infinite series and diverging infinite series. Now, let's talk about infinite geometric series. Take a look at the first example, the 2 plus 4 plus 8 plus 16 and so on. And the second example, the S sub infinity equals 16 plus 8 plus 4 plus 2 plus and so on. We denoted them by S sub infinity because you are adding infinite number of terms. We are having infinite series here. The first one is, take a look, the common ratio is 2, and 2 is higher than 1. So this series is diverging. For the second series, 8 divided by 16, 4 divided by 8, 2 divided by 4, has a common ratio of 1/2 or 0.5, which has an absolute value between 0 and 1. Hence, this series is converging. And the thing is, what can you say about the sum of each? Is the sum of the first one finite or infinite? How about the second one? If you could see from the first series here, the terms that you are adding keep growing. They're becoming bigger and bigger. And therefore, if you will be adding infinite number of terms, you have to expect that the sum will be infinitely large. That is why if you have an infinite diverging geometric series, expect that the sum will be infinite. I mean, or if it's not infinite, or maybe it's something that you could not determine, or the limit is not finite. However, for converging geometric series, it is finite. And I will explain later how come the sum of an infinite converging geometric series is finite. So again, infinite converging geometric series has a finite sum, whereas an infinite diverging geometric series does not have a finite sum. So for our lesson today, we will be interested more about infinite converging geometric series, and we will be determining its finite sum. And we will not discuss much of infinite diverging geometric series because the sum is infinite or not finite. Now, suppose I give you this. Remember, our topic is all about infinite converging geometric series. So ask yourself first, is this series geometric? If you could see, you could verify with the help of your calculators. 2 divided by 3 is 2/3. 4/3 divided by 2 is 2/3. 8/9 divided by 4/3 is 2/3. So this is geometric. Is this infinite? Yes, because is this converging first? Yes, because the common ratio of 2/3 is between, the absolute value of that is between 0 and 1. Is this infinite? Yes, because you have a first term, but you don't have a last term. So again, this is indeed an infinite converging geometric series. So note that before doing the next steps for this particular case, you have to make sure that indeed if it is infinite, if it is converging and geometric all at the same time. If it does not satisfy all of those conditions, then I suggest that you do not do this next step. Now, let's find the sum of this. We don't know the exact value, so for the meantime, let its value be S sub infinity equals 3 plus 2 plus 4/3 plus 8/9 plus dot dot dot. You could see that the common ratio here is 2/3. And so the technique here would be multiplying both sides of the equation by 2/3 or whatever your common ratio is. So 2/3 times S sub infinity is 2/3 S sub infinity equals 3 times 2/3, it's 2. 2 times 2/3 is 4/3. 4/3 times 2, it's 8/9. 8/9 times 2, it's 16/27 plus and so on. And what do we do next is that you could see that there are common terms that are 2, 4/3, 8/9, and so on. Sir, you might say, sir, there's no 16/27 here. No, remember, this is infinite. So it's understood that there is a 16/27 as a term here. And in fact, all the terms starting from 2, 4/3, 8/9, and so on, going to the right, are basically the same terms here. That's why we will be subtracting both sides of the equation to eliminate those terms that are common. Doing such, we align the terms that are the same. It's understood, by the way, that there is a 0 there. It's already implied. It's understood also that this number here is 1. 1 minus 1 S sub infinity minus 2/3 S sub infinity is 1/3 S sub infinity. 3 minus 0 here is 3. And the 2, the 4/3, 8/9, and so on will become 0. Hence, 1/3 S sub infinity equals 3. Multiplying both sides by 3 to solve for the value of S sub infinity, you get S sub infinity equals 9. Hence, or thus, 3 plus 2 plus 4/3 plus 8/9 plus dot 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 is equal to 9. So this implies that, for example, if you will be given an infinite number an infinite amount of time to add all of the terms. If you will continue the pattern and add all of the terms of this series, expect that the sum will never be greater than 9. Hence, we could say that the limit is 9. I will not focus more on limits because I don't want to spoil you in your calculus lessons. But for now, at least you have an idea, a slight idea of what it is. So you see, this infinite converging geometric series has a finite sum that is 9. If you wish, you could verify with your calculators. Try adding as many terms of this infinite converging geometric series, and I'm sure your answer will never be more than 9. I hope it's clear with us. Now, let's derive the formula. Suppose we have here S sub infinity equals A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 plus dot dot dot. And we know that the explicit form of the terms of your geometric series are the following. A sub 1 is still A sub 1. The second term is A sub 1r. The third term is A sub 1r squared. The fourth term is A sub 1r cubed, and so on. You could, if you would like to check, you are free to visit our videos about the explicit form of the terms of a geometric sequence. And using a similar method by multiplying both sides with a common ratio, we get r s sub infinity equals a sub 1 times r will be a sub 1r times r here will be a sub 1r squared. Multiplying by r, a sub 1r cubed. Multiplying this by r gives you a sub 1r to the fourth, and so on. It's understood again that after this, you have other terms because of your ellipsis. So it's understood that you have a sub 1r to the fourth here, and so on. And so all of the terms starting from a sub 1r and the rest are the same here. And what did we do again earlier? We align those terms that are the same, and we will subtract both sides of the equation to eliminate terms that are the same. So S sub infinity subtracted by r S sub infinity gives S sub infinity minus r S sub infinity equals a sub 1 minus 0 here. So that's a sub 1. A sub 1r minus a sub 1r will be 0. In fact, everything here will become 0. That's why you have this. We could see on the left-hand side that S sub infinity is a common factor. Factoring out S sub infinity divided by S sub infinity is 1 minus r S sub infinity divided by S sub infinity is r. That's why the left-hand side is equal to S sub infinity times the quantity 1 minus r equals a sub 1. Since we don't need the value of 1 minus r on the left-hand side, we have to divide both sides by 1 minus r, thus giving us S sub infinity equals a sub 1 all over 1 minus r, where again, I have to emphasize that the absolute value of your common ratio is between 0 and 1. So this is now the formula of the sum of the infinite number of terms of an infinite converging geometric series. But what I showed you here is kind of weak. So I will be presenting to you for me, a better argument. Recall the partial sum of a geometric series formula. S sub n equals a sub 1 times the quantity 1 minus r to the n all over 1 minus r, where r is not equal to 1, because if r is 1, then your expression becomes undefined. Where S sub n is the sum of the first n terms, n is the number of terms, a sub 1 is the first term, and r is the common ratio, but again, not equal to 1. And this is only applicable for finite series. Now, how about if we have infinite series? Or for the meantime, how about if our common ratio has an absolute value which is between 0 and 1? For example, without loss of generality, let's say I let my common ratio be 1/10. If I raise 1/10 to 1, you will get the 0.1. If you raise that to 2, you will get 0.01. If I will raise 1/10 to 3, you will get 0.001. How about if I raise that number to 10? I will get this number, then you have here 9 zeros followed by a 1. And if you could see, as we increase the exponent of your common ratio, for the meantime, let's have a positive common ratio. If we increase the exponent of your common ratio, what have you noticed with the value? It becomes smaller and smaller and smaller. And how about if you use your calculators with you, if you try 1/10, raise that to 1 million, what value does your calculator give you? Correct me if I'm wrong. Your calculator displays 0. Please check. And the thing is the answer or is the value of this expression really 0? No. Probably in this case, the value is not really 0. It's just that the number is so small in value that it is very near or approaching 0. We could see that as the exponent increases, the value of your r raised to n, where r here is your common ratio whose absolute value is between 0 and 1, and n here is let's say an exponent, let's say a natural number or a whole number, then r raised to n approaches 0. When I say approaches, it's not really 0, but this number keeps getting and smaller that it's very close to 0. That is why if you are given this formula, if the absolute value of your common ratio is between 0 and 1, then r raised to n approaches 0 as n approaches infinity, or as n becomes very, very, very large. And that's why if we let r, so we say in this case that the limit of r raised to n here is in fact 0. For the meantime, I'm sorry, I could not really teach you about limits because that topic will be reserved when you go to senior high school, particularly if you will be pursuing STEM. But for the meantime, letting r raised to n equal 0, since r raised to n approaches 0, we get, in this explicit form, you will get s sub n replacing n by infinity because we are approaching that value. S sub infinity equals a sub 1 times the quantity 1 minus 0 all over 1 minus r. 1 minus 0 is equal to 1. In the numerator, that's a sub 1 times 1, it's a sub 1. And you could see, copying the rest, we have s sub infinity equals a sub 1 all over 1 minus r. But again, I would like to emphasize that the absolute value of your common ratio here has to be between 0 and 1. Your series, your infinite geometric series has to be converging. Because if it is diverging, or if it has a common ratio larger than 1, then this formula will not work. Hence, ladies and gentlemen, the sum of an infinite converging geometric series formula is S sub infinity equals A sub 1 all over 1 minus R, where S sub infinity is the sum of the infinite number of terms of your geometric series. A sub 1 is the first term, and R is the common ratio between 0 and 1. All right. Let's do this. So going back to the example I gave you earlier and applying the formula, we could see that the first term or the first number here is 3. And the common ratio is, let's say, 2 divided by 3, it's 2/3. And 2/3 is between 0 and 1. This is an infinite converging geometric series. Applying this, we have S sub infinity equals 3 all over 1 minus the common ratio, which is 2/3. 1 minus 2/3 is 1/3. And this becomes 3 all over 1/3. If you divide by 1/3, it's the same thing when you are multiplying the numerator 3 with the reciprocal of 1/3, which is 3. That's why you have 3 times 3, and that is 9. And S sub infinity is 9. And therefore, you could see earlier, using the technique we had earlier and using the formula for an infinite converging geometric series, we get a finite value of 9. I hope you got it. Now, let's have some more exercises. Let's have the exact value, find the exact value of 5 plus 3 plus 9 fifths plus 27 fifths and so on. The first term here is 5. You could verify that the common ratio here is 3 fifths. So 3 divided by 5 is 3 fifths. 9 fifths divided by 3 is 3 fifths. 27 25ths divided by 9 fifths is 3 fifths. Solving for S sub infinity, we have this formula again. That's S sub infinity equals 5 all over 1 minus 3 fifths. 1 minus 3 fifths simplifies to 2 fifths. So we have this expression. S sub infinity equals 5 all over 2 fifths. If you are dividing by 2 fifths, that's the same thing when you are multiplying with 5 halves. So this becomes 5 times 5 halves. That's 25 halves or 12.5. I hope you got 25 halves or 12.5 or 12 and a half. And if you did, great job. How about the number? Let's have another example. Suppose, express as a proper fraction the non-terminating decimal 0.35, dot. Probably you have learned that in your grade 7 or in your elementary, right? And your teacher told you that there are certain techniques how to do it. But don't worry, it is also an application of an infinite converging geometric series. So for the solution of this, we know that this non-terminating but repeating decimal could be expressed as the first 35 here is 35 over 100. The next 35 here, you have here 1, 2, 3, 4 decimal places in all. That's plus 35 over 1 followed by 4 zeros. So 35 over 10,000. The third 35 here is 35 over 1 million plus and so on. Remember, you could continue this pattern indefinitely. So you could also continue this. You have an infinite converging geometric series with the first term of 35 over 100 and a common ratio of 1 over 100. You divide the second by the first or the third by the second and so on. You will get a common value of 1 over 100. So solving for S sub infinity, S sub infinity equals a sub 1 all over 1 minus r. By substitution, that's 35 over 100 all over 1 minus the common ratio of 1 over 100. 1 minus 1 over 100 simplifies to 99 over 100. So you have this 35 over 100 divided by 99 over 100. But dividing by 99 over 100 means you have to multiply the 35 over 100 with 100 over 99. 100 divided by 100 becomes 1. You have here 35 over 1 times 1 over 99, or that's 35 over 99. Thus, this non-terminating, this repeating and non-terminating decimal, 0.35, 35, 35, and so on, is just equal to 35 over 99. You could verify that with your calculators, or you could check that what you have learned today or what I discussed right now is consistent, has a consistent answer with what you discussed when you were in grade 7 or when you were in elementary. Let's have another example of another application. Evaluate the summation of 4/5 to the nth power as n goes from 1 to infinity. You could see in this particular summation expression that your lower boundary or your lower limit is 1, and the it goes, you have infinite number of terms because of this infinity symbol. So with that, the first term, to get the first term, of course, you will let n be equal to 1. 4/5 raised to 1 is 4/5. The second term is 4/5 quantity squared. The third term is 4/5 quantity cubed, and so plus and so on. We have to add all of them because we are talking about summation. You could see that the first term here is 4/5. The common ratio is also 4/5. And solving for S sub infinity, we have S sub infinity equals a sub 1 all over 1 minus r. That would be 4/5 divided by 1 minus 4/5. 1 minus 4/5 simplifies to 1/5. That's why it becomes 4/5 all over 1/5. This is equal to 4/5 times 5 over 1. 5 divided by 5 here becomes 1. And your final answer here is 4. Hence, the summation of the quantity 4/5 raised to n as n goes from 1 to infinity is 4. I hope you got it. And if you did, great job. But if not, at least it's a good learning experience for you. Number 4. This is our last example, I believe, for this video. Solve for x. 1 plus x squared plus x cubed plus ... equals 5. You could see from this expression, you might ask, sir, is that an infinite converging geometric series? You might ask. And the answer is yes. You could see from here that the first term is actually 1. If you divide the second by the first, x divided by 1 is x. X squared divided by x is x. X cubed divided by x squared is x. So you see, you have a common ratio of x, provided again that your common ratio is not equal to 0, or else you will have an undefined common ratio if that happens. And 5 here is the fixed sum. So S sub infinity here is 5. Solving for x, S sub infinity equals a sub 1 all over 1 minus r. S sub infinity will be substituted by 5. And a sub 1 will be substituted by 1. And this gives us 5 equals 1 all over 1 minus x. Multiplying both sides by 1 minus x to clear of fractions, we have 5 times 1, 5 here. 5 times negative x will be negative 5x equals 1 will be left on the right-hand side. Subtracting both sides by 5, you get negative 5x equals negative 4. To solve for x, we have to divide both sides by negative 5. So x equals negative 4 divided by negative 5. Negative over negative is positive. So x is 4/5. So you see, the value of your x here, or your common ratio, is 4/5. I hope you got it. And if you have questions or clarifications, feel free to comment it down in our comment section, or feel free to message me in my social media accounts. With such, please answer this practice set. You are free to work by pairs. I will allow you to work by pairs. So this is by partner. And the usual thing, both of you will help each other in answering this. However, each one has to pass or PM to me your work, your complete set from 1 to 5, hopefully within this day. And don't worry, these items are somehow, most of them are parallel with what I gave you. And with that, thank you so much. I hope you learned something from this video, and a great day to one and all. God bless everyone.